Hi everyone, this is Morgan. So we are talking about the organic reactions. It's the organic outline, page 7 and 8 for Honors Chem. We're going to be looking at some different types of organic reactions. We're going to classify them very similarly to what we did back in the fall with just normal reactions. So, combustion. Combustion is where you take a hydrocarbon like CH4 and you burn it with O2 and it produces CO2 and H2O. We don't worry too much about balancing when we're doing organic reactions because they almost always balance in a 1-to-1 ratio. This combustion doesn't, but most of the others will. Now, we need some type of catalyst to make this reaction happen. I can release methane in the room, and it will sit there and it won't burn until a spark. Okay, so we need some type of spark as the catalyst. We'll write the catalyst over the arrow. Substitution. Let's take CH4. And when we're dealing with substitution, halogens are wonderful examples. Almost all of the examples for this will be with a halogen. One hydrogen comes off and a bromine goes on, and then we end up with HBr. Now, this is an incredibly cool reaction because the actual catalyst is visible light. H-nu, okay, is how we would indicate visible light. That comes from the formula E equals H-nu, or the energy of electromagnetic radiation. Okay, addition. In order to have addition, we're going to have a double or a triple bond that we can break open. And again, it's going to be halogens we talk about all the time. That double bond opens, and what happens is we get the hydrogens all there, and then a bromine on each of the carbons. Because when that double bond breaks, there's an electron on this side, there's an electron on that side, or one on this carbon and one on that carbon, and that's the spot where the BRs add on. That turns out a metal, and a metal meaning something like platinum or palladium or rhodium, okay? A non-reactive metal is the best catalyst for that. All right, hydrolysis. Well, hydrolysis is also an addition, but you can probably figure out from the name that what we are adding is water. So we end up getting, by the way, it's a metal again, we end up getting an OH group added to one end and then just a hydrogen to the other end. And that's what happens. Dehydration is the removing of a water. So we'll talk about esterification. There are a lot of different dehydration reactions, but we're going to do one that's a dehydration esterification. What we need to start out with is a carboxylic acid, like acetic acid, reacting with an alcohol, like methanol. We need a dehydrating agent, 98% H2SO4, or concentrated sulfuric acid. And what happens is that this OH group hooks up with that hydrogen, okay? And what we end up getting is an ester and water. Okay. Next page, all about polymers. Many molecules. Okay? Poly many, mer unit, or molecule. There are several different types of polymers. We'll start off with an addition where we add together two of the same units, like ethylene. We'll make polyethylene. in the presence of a metal, because again we're breaking open a double bond. Carbon, 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 double bond, carbon. And then repeat. And do it over and over and over again, and this can become really, really, really long. Okay? One you might know about from AP Bio, the peptide bond. What we're going to do is we're going to start off with H2NC with an R group, with an H, C, double bond O, OH, which looks suspiciously like an amino acid, reacting with another amino acid, H2NC, we'll call it R prime. It can be the same amino acid, it can be different. And what happens is one of these H's and this OH form water. And you can use a metal for this also. Actually, the best is going to be to use enzymes. And we get H2NCRH, C, double bond O, and then that's going to go straight to a nitrogen, which has a hydrogen, which goes to the carbon with R prime, down here in H, C, double bond O, OH, and that right there is what we call the peptide bond. Okay, now, polyester. Many esters. And this was very popular back in the 1970s for really bad clothing. What we're going to need are some symmetric molecules. So HO, C, C, OH, with hydrogens coming off it, reacting with HO, C, double bond O, so we have alcohol, and we're going to have carboxylic acid, ester again, right? Except this is actually bonded to a benzene style ring. Okay, boom, 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 boom. Double bond, single, double bond, single, double bond. And that carbon goes to a carbon that has a double bond O to an OH, so it's got a carboxylic acid on either side. This has got an alcohol on either side. And we'll do the same thing here again with the alcohol. All right, so using all of the right catalysts, what we end up with here are two water molecules, because what happens is we get reaction here and we get reaction here, which forms waters, the two waters, plus HO. C, C. Then over here, we're going to get an O to a carbon that's a double bond to an oxygen that has the benzene ring. And then the double bonds will be there, there, and there. We got some hydrogens coming off. This is going to go to a C, which is double bonded to an O, to an O, and then that goes to a C, hydrogens coming off, and an OH right there. Okay, and this one, when it just happens over and over and over again, is referred to as Mylar or Dacron. Okay, there you go. Those are your basic organic reactions. Thanks for tuning in. This is Morgan signing off.